Hi, everyone. Thanks for the invitation from committees, and it's great that I can share some of the research results that I had in talk from the Mars Society. So I will mainly talk about some few new tricks in solicited MR, and the three new tricks are three well-established code sequences. And with some modifications on the well-established code sequences, we can more accurately extract structural informations. So I'll start with some recent hardware developments in classical solicited MR, meaning that I didn't include DMP inside. So these are pictures taken from Max Planck Institute for multidisciplinary Naturwissenschaft in Germany, and the availability of the 1.2 gigahertz. And for solicited MR, the availability of 0.7 millimeter rotors, which we can spin the sample up to beyond 100 kilohertz. These are the recent hardware developments in the field. And with the development of hardware, this enables enable us to extract structure, to determine the structure for larger and more complex biosolids. So here I sketch a plot. In the axis is the year, and also I noted here some of the significant events happens in the year, the availability, including the availability of 1 gigahertz magnet and 1.2 magnets. And also on the y-axis is the size of membrane protein that is solved by solicited MR method. And as you can see that with the availability of higher field and the faster spinning probes, we are able to solve bigger and bigger proteins. One thing worth noticing here is that in the past 20 years, we have increases of approximately 200 megahertz every 10 years. And I hope this trend will continue, because we then definitely benefit from higher magnet. Yeah. And here I show a comparison of the spectra obtained from 1.2 gigahertz and 950 megahertz fields. The sample that we use is M2 membrane protein. As you can see that we gain in resolution not only in ppm value but also in absolute hertz values. So our line get actually sharper. So with the availability of better and better improvements, we will also need pulse sequences that is suitable for different fields and different MS spinning speed. And also, actually, for solicited MR, each sample has its own different situation. We need to design the pulse sequence according, even though some it's well established, but that doesn't mean that it's suitable for all situations. And there are definitely cases, different factors we need to consider. So the first example here, I will propose a scheme that's more efficiently use all signals in XHH sequence. XHHX is a scheme that is normally used in solicited MR to extract long-range distance contracts. So as you see here on the left side of the spectra that is obtained, that is a homonuclear spectrum. We normally observe these autocorrelation peaks. And this autocorrelation peaks is normally a few times more intense than the structurally important mixing peaks, cross peaks. And these strong autocorrelation signals sometimes obscure the nearby peaks of interest. So to solve these problems, people sometimes use single quantum and double quantum spectra. With a good dispersion in the double quantum dimension, we may solve the peak overlap. But the problems for single quantum double quantum spectra is the efficiency of double quantum of this scalar or Doppler coupled spins. The efficiency to excite this double quantum coherence is actually decreased with if the distance in between the spins are far away to each other. And our aim is actually to see an interesting peaks for us is actually long range contacts. And also for dark spectrum, this group from Riqiang Fu's group, they propose some phase cycling, and with the reconstruction of the spectra afterwards, they managed for a dark spectra, they managed to have something diagonal free. But this is specific for one scheme, and also extra, since we need to reconstruct for the spectra, extra scans were needed, which doesn't contribute to the final sensitivity of detection. And based on proton detection, the single-quantum recoupling schemes like RFDR is commonly used. And Professor Lin's group, they proposed a scheme in 2014 to suppress the strong autocorrelation peaks in SH3 in a 4D spectra, and they demonstrated on SH3 sample, on protein sample. So the idea for this scheme is actually also to sum the signals from non-mixing spectra and also mixing spectra, and by place with the phase cycling to have a complete subtraction of the autocorrelation peaks. And they managed to have the spectra completely diagonal free. And they stated here with per digit sample, 25% back exchange protein, non-mixing scans versus mixing scans is 1.2, the scan that is needed. And if it's 100% back exchange, the scan that is needed for non-mixing, and mixing is 1/4. The spectra is very nice, and this is a very good scheme, but also the downside of it is extra scans needed. So this scan doesn't contribute to the final sensitivity of detection. So what we proposed here is a small modification on CHHC or NHN scheme. So on the left side here is the pole sequence. We have a single transfer to CP from H to N, N to H, and mixing H to N again, and N to H, and then backward detection. So in your original pole sequence, we do not have these two pi pulses. After the CP transfer here, we have most of the polarizations transferred from nitrogen to proton, but actually but these CP transfer are normally not complete. We still have some polarization that is still left over on the nitrogens. And since the signal is on X, the T2 is very short compared to T1, and this signal simply just disappear, and we don't make use of these signals. And then when signal transfer from CP H to N here, it's this signal simply decreases with T2. But somehow we can preserve this signal. This we call these leftover signals often spin operators. We can make use of these signals by flipping back to Z, and naturally T1 is long, then this signal is preserved. And since in this region, N-spin diffusion is very inefficient at faster spinning, so this signal here only contribute for the autocorrelated peaks. And if we make a negative sign, and when we sum up for this transfer pathway here, we can subtract peak intensities in the diagonals. So we also demonstrated this scheme using SH3. It's a deuterated protein, and we spin it at 55 kilohertz. As you can see here, for the diagonal peaks, we managed to have approximately 50% of suppression while not sacrificing peak intensities at the mixing region. So apart from proton detection, we would assume that when it comes to carbon detection, the situation would be the same for the CHHC. But actually, the situation is a little bit different because of a recoupling condition called PAR condition. PAR is a third spin assisted recoupling condition. To achieve that condition, the form in the pole sequence is very similar to CP. You have two CW pulses here, but the power that you set on the CW pulse, it's a bit different from CP. So on the right side here, we show a simulation. X-axis is the power we set on carbon or on nitrogen over the Rother period. On the left side is the power that we set on the y-axis is the power we set on proton over Rother period. All these black dotted line here are actually the CP conditions. N equals 0 and equals +1 -1 CP condition here. And the color-coded map here is our power condition. So you can see here is our power conditions. So when we are at slower spinning and with a 90 to 100 ramp on the proton, we actually have the power on proton cover for this length here, and denoted in red arrows. So since the MS is very slow, with a ramp we easily during the CP time also covers the power condition. This is actually not a problem for faster spinning because our MS is fast. Then the power that we set on protons are let's say 50 kilohertz or 100 kilohertz. So even with the ramp, this arrow region is still very narrow and doesn't touch the power conditions. Meaning that our signal pathway, the valid signal pathway here, are not the same as what I introduced previously. Autocorrelation peak is actually a power signal, not only autocorrelation, but power recoupled. We can make use of it by phase cycling CHC signals minus R, and with that we obtain an active diagonal peak actually. But actually we can also use it in another way, CHC plus these PAR conditions, and we enhance in general the sensitivity of the experiments. So we actually combine in one pole sequence, we can combine two these schemes, which is related with the long range, which enable us to extract long range contacts in solid state NMR measurements. Yeah, so this is the first trick I would like to introduce. And the second one is actually a modification on widely used heteronuclear correlation spectra. So the sample that I'm using here is actually different from, it's not a protein sample, it's a polymer sample, it's polystyrene. So what we observed is that for polystyrene sample, with the addition of different ions, it will be able to change the glass transition temperature of this polymer, especially for the case of addition of lithium chloride. This change can be more than 20 degrees. So what makes it different from other ions? In a simple proton 1D, what we can see is that lithium chloride actually absorb water and introduce a lot of extra water in the system. This is very different from other salts. So our guess would be that the reason for this large change in the glass transition temperature is due to the introduction of also is the ion carry water inside of the polymer. So to prove that, since this is a three-component system, we have water, we have polystyrene, we have lithium. So prove that, we need to prove that water is close to the polymer, and we also need to prove that water is close to the ion. So in order to prove that water is close to the polymer, we use this hardcore correlation experiment. But we started this experiment with the T2 filter. We can see from this spectrum here, proton signals from the polystyrene, they're actually much broader than water peak. So water definitely have a much longer T2. We want our initial signal to completely come from water, and through a spin diffusion and CP transfer, we can have the signals from water and correlate it with carbon sites on the polystyrene. And this is what we observed. And since this is a distance reachable by spin diffusion, so we think it's the distance in between protons from water and the protons from the polystyrenes are something like within 5 angstroms. So after this proof, we also would like to prove that water is close to the ion. Then we just use, first of all, we also need a T2 filter to make sure that our origin of the signals are all come from the water. And then we use a CP, and on the 7 lithium spectrum, we see a peak here. When this work comes to this point, we still have 2 points to solve. One is what's the binding mode for lithium to water, and also since glass transition temperature, polystyrene has been changed. So does the ion really have an impact on the side chain packings or dynamics of the side chains in the polymer? So we continue this study. In this spectra here, with the CP transfer from protons to lithium, we observe a signal. But when we try to detect this signal in 2D, we found that that peak is halfly real or half fake, because obviously there are excess ion signals exist in the system, and these ion signals escape the phase cycling and give rise to a T1 noise in the spectrum. So in order to have an analytical analysis of the peak intensity in here, we need to suppress this T1 noise first. So in here, we repurpose a scheme for Mississippi pulse sequence from solvent suppression to and add it here for the aim of ion suppression. And normally for solvent suppression, we will need 100 milliseconds to 300 milliseconds as the length for ion suppression. But interestingly here, we only we need approximately 1 second in order to fully suppress these ion signals. And as you can see on the right side here, with the addition of this ion suppression block in pulse sequence, we have a clean peak only. So with a clean spectra, then we can analyze the signal buildup due to CP. The lithium to water binding mode is actually has been studied for quite a long time, and since lithium, both protons and lithium, quite light for X-ray, only until 2016 and 2017, synchrotron gives some structures which I think is more reliable and for the binding mode. But we all know the problem for the synchrotron, they are not as flexible as us associated NMR, because we are less picky about sample status. So so in this work here, actually I only want to verify 1 point from simulation, because DFT people, they actually made these simulations and proposed 2 possible modes for the lithium to water binding. If this interaction between water to lithium is driven by charge affinity, then the distance in between lithium to a proton is actually approximately 2 angstroms. And if it's actually driven by an energy term called cross exchange energy term in between lithium and oxygen, then the distance in between protons and lithium is approximately 3.6 angstroms. And these differences, if we measure Doppler coupling, the differences in the curve will be, as we show here, it will be very clear in solid state NMR. So what I measured here in this 3-component system, it's a Doppler coupling of approximately 11.4 kilohertz, which corresponds to approximately 1.6 angstrom. But I will probably not interpret it into a distance here, because the system is complicated. We probably have more than 1 spins inside, and also water in the system definitely goes certain motions. And what I measured here is actually an average interactions. But what can be say here is that since this Doppler coupling is so large and definitely matches more with the with the interaction driven by charge affinity. So I verified this interaction is more driven by charge affinity, and give this model to my DFT collaborator. They put it into simulations and found it out that by adding the number of waters in the system, actually the tandem pi interactions between lithium and aromatic ring can be quenched once once this water number exceeds 4, because the water to lithium interactions are so strong, they actually quench the tandem pi interactions in between lithium and aromatic ring. We found it out in our system by measuring proton 1D. So in here, the red one, it's the measurement before we leave the sample in air for some time, and in blue, it's the sample that is the proton 1D that we measured once we leave the sample in air for some time. And we measure these two status, the same sample just before leaving to air, after exposed to the air. We found that when it's not exposed to air, yes, we observe a big transition of gas transition temperatures. After we leave it in air for some time, it actually moves back. So this would be an indication of kind of interactions is actually quenched. So, but at this point, still we have one more question to answer. Yes, probably we can say that our lithium is very close to the aromatic rings, the side chains in the polystyrene. We can say that in terms of property, we saw something there, but we don't know if this addition of lithium actually changed the structure or the dynamics in the polystyrene. We didn't show any direct evidence to prove that polystyrene has changed. To show that, we actually resort to chronotactic experiment. So we put our sample to do proton 1D, because whenever it comes to this type of sample, we always, and we want to do proton detection, we always comes to have our own question: how fast should I spin? So we try to increase MS 40 kilohertz until 90 kilohertz, and we can see that for the aromatic region, probably 60 to 70 kilohertz is already enough, and further increase in MS frequency doesn't give that much of an effect as it is for the aliphatic regions, for the PIC2 regions. This is definitely related with the proton-proton Doppler couplings, the local Doppler coupling environment, and we resort to a concept that is proposed from by Brown and Hodgkinson in 2006. They call it DRSS. It's actually, let's say we have a proton spin here. The Doppler couplings in between these protons on one side and second side, we take the square of them, and for all the protons nearby this these protons on one side, we sum them up and then make a square root of the sum and calculate the value. We found it out that for aromatic protons, they have much, and also the CH group, they have much less DRSS values than the methylene groups on the second side. That's why actually they need that's why CH2 group needs much faster spinning speed in order to obtain optimal line width. And actually, these CH2 group methylene groups, they actually have a very similar to DRSS values as the CH3 groups. And for the CH3 groups, for the methyl groups, how fast it is needed, we actually discussed in a series of papers previously. But anyway, in our sample, for this sample, actually I decided to use 90 kilohertz as the spinning speed because I don't need to chase for, I don't need to go after for the real optimal resolution, because this system is not as large as floating systems where I have really many temperature predictions needs to be resolved. Yeah, this is the spectra that I have for the polystyrene. I recouple proton-proton Doppler couplings using RFDR and obtain this mixing peak from protons from first side to third side and from third side here. In order to verify that the distance in between this backbone to the sidechain is different, actually I measure the RFDR curves, time-dependent RFDR curve for the polystyrene sample alone and polystyrene sample with addition of lithium chloride, and observe these two different curves. Since this is a system very complicated polymer structures, it's stochastically stacking of the and the entanglement. The system is very complicated, and what we observe here is only an averaged an averaged signal. So I would not interpret this FDR curve directly into a distance. But what we can definitely see here is with the addition of lithium chloride, the structure or the dynamic of this polystyrene has been changed. So yeah, the third one that I would like to introduce here is Codex, and with the application of some crystals. So Codex is a scheme that used in solar system R to quantify slow dynamics, and it's actually invented by Schmidt-Rowe in 2005, and later also shown by Mahon in 2006, that it can be used to count the numeric numbers. So the idea of it is actually to encode and decode the orientation-dependent CSA. And in between, we have a spin diffusion. So in terms of sample, we selectively isotope enrich so this is a demonstration of phenylalanine. We selectively enable on only one site in the whole molecules. And experimentally, what we observe would be a spin diffusion time-dependent curve. This curve will have an exponential decay and then reach a plateau. The plateau value here will tell you that how many spins they are actually close to each other. So if I have two phenylalanine molecule here, and this labeled spin, they have different CSA, I mean their orientation is different. We have the spin exchange in between, polarization exchange in between these two spins, and then we will have the curve decay to half, and we know that yes, we have two spins close to each other. And if we have three spins, then the curve will decay to 1/3 and how fast and this exponential decaying behavior is related with the Doppler coupling, and then in other words, with the distance in between these two spins. So what we found is that, yeah.
Can I just draw your attention to the time?
Yeah.
Quickly, if you could round up. I know you're very close to the end anyway. I just wanted to draw your attention. That's all. Thank you very much. It's really interesting.
So what we show here is that for glycine, our curve decays to half, and for phenylalanine hydrochloride, it decays to approximately 0.24. But for the phenylalanine that dissolved in water and crystal forms at neutral pH, which from paper we know that is from crystal study, we know that it should be decaying to 1/8. The prime value is 8, but we observe something to 0.109. This is actually because although our sample it's isotope enriched, but on our other side, 13C is not depleted. It has approximately, for 13C, it has natural abundance, approximately 1% of it. And since we have 8 natural abundant spins nearby, then what contribute this natural abundant spin contributes to the decay. It actually have an error range of 1% times 8, approximately 0.08. This is not a big problem to differentiate if the Z prime value is 4 or 3, but when it comes to 8, 9, 10, when we see plateau value to 0.125, 0.111, and 0.10, it will be confusing. So we propose that we have a pre-equilibrium part before the encoding and decoding of CSA. And then we know that we don't, after the CP and equilibrium, all the polarization is equally on all the natural abundant spins, and then we can back calculate to compensate for this effect. So this, although this is the last slide, but I think this can give us a very interesting number here, because for we actually do this paper to verify a structure, crystal structure that is determined by crystal people in 2014, although it's phenane crystal, which is studied for quite a long time, but phenane is very interesting and unique. They form different crystals according to a lot of crystals according to variations of crystallization conditions. And in our system, when we selectively label carbonyl sites, we have decaying curve reach approximately 20% of the signal and reaches plateau. Only if we label on the gamma site, we reaches this 10.9 plateau, which indicates the Z prime value of 8. This is because all our spin diffusions is rely on the direct spin transfer and also relay transfer. But if we label on the carbonyl side, this the distance in between these two clusters, that's the distance is 12.45 angstroms, which carbon-carbon spin diffusion cannot, when it comes to more than 12 angstroms of distance, this spin diffusion becomes so inefficient that we don't see the signal transfer from this side to this side. That's why only if we label on the gamma side, we will be able to see it. That's it. These are the three small tricks that we have on the established code sequences, and I hope you like it. And all this previous work cannot be done without help from my previous colleagues from MPI, Dr. Laura Antias, Christian Grisinger, and Evgeny Nemirovsky, and Dr. Kuma Tekvani, and also from my PhD group from TULM, Professor Ben Reif, Dr. Rita Masaka, and Shenik Tosla, and also my collaborators from Peking University and Nanyang University of Technology here, Prof. Tang Chuan, Prof. Fan Tuan, Dr. Ye Hong, Dr. Wenpeng Lu, and also team members here, Ms. Qin Zeyuet and Ms. Ye Kai. And thank you for your attention.